Welcome pre-cal students to the homework help video. The assignment is here in front of you, and let's go ahead and get started. Feel free to fast forward ahead to the ones that you had problems on. Let's first of all take a look at numbers 1 and 3. The directions say to find the inverse of the relation, okay, for numbers 1 and 3. Well, if you took notes on the lesson and listened well, you would know that by definition, the inverse of any given function or ordered pairs is when you simply just flip-flop the domain and range. So if the function we're dealing with had 7, 8 for one of its points, then on the inverse function, the point 8, 7 would exist. And so obviously another point that would exist on the inverse graph would be 8, -2, and another point would be 4. And my pen is really doing some weird things, students, so sorry about that. It'd be -4, +3. And then also -8, 8. Okay? Alright, so all we did was we took each ordered pair and we just flip-flopped the domain and range. Alright, number 3. Well, if -1, -1 existed on the given function, then the inverse function would also have this ordered pair. And then the inverse function would also have this ordered pair. Okay, again, you just flip-flop the domain and the range. Now, for numbers 5 through 10, the directions ask us to find the equation of the inverse relation. Okay, so we're trying to find an inverse equation. Well, let's start with number 5. What you were taught to do is everywhere there's a y, we're going to put an x. And everywhere there's an x, we're going to put a y. Now, in the back of the book, this is as far as they went, and that's fine. For me, I do want you to get y by itself. That's very important to me to do that. So, bring the 5 over and make it a +5, and now you're left with x plus 5 equals 4y. And now we're going to divide each term by 4 to get y by itself. And of course, don't forget there's a 1 in front of the x. So 1 divided by 4 is 1/4 x. 5 divided by 4 is 5/4. And then 4 divided by 4, your 4's would cancel, leaving you with y. So let's look at this again. Step 1, everywhere there's an x, you put a y. Step 2, everywhere there's a y, you put an x. And then step 3, get the y all by itself. All right? Moving on to number 6. Well, 2x squared, so I'm going to put 2y squared, and then I have 5y squared, so I'm going to put 2x squared equals 4. And now let's get the y all by itself. So the first thing I'm going to do is bring the 5x squared over, and when I do, it becomes a -5x squared. Now divide every term by 2. If I divide this term by 2, I'm left with y squared. 4 divided by 2 is 2, and 5 divided by 2 is 5/2. And then lastly, I take the square root of both sides. So again, I'm sorry, my pen is messing up. And now we take the square root of both sides. The square root, and by the way, why do I do that? Because I want to isolate the y. I want to get y by itself. And right now, I have y squared. Okay, and I don't want y squared. I want just y. So the square root of y squared is y. But if I take the square root of one side, I must take the square root of the other side. And don't forget your plus minus. Okay? So there we go. Now the back of the book, of course, left their answer like this, and I'm not going to allow that on tests and quizzes. I do want you to isolate the y. Okay, moving on to number 7. Okay, I have an x cubed, so I'm going to put y cubed. Then I have an x or a y, so I'm going to put an x right here. And then equals -5. Now I want to get y by itself, so the first thing I do is I divide both sides by x. Now a lot of students might have thought there that you should bring the x over and make it negative, but these two are one term. They're tied together. They're multiplying. You can't just split them by moving part of a term. You have to divide both sides by x. So here your x's cancel, leaving you with y cubed equals negative 5 over x. And then next we take the cubed root of both sides because I have y to the third power. Well, the cubed root, like this, the cubed root of y cubed is y. But if I take the cubed root of one side, I must take the cubed root of the other side. And the cubed root of negative 5 over x would just simply be this, okay? So there we go. There is my inverse function. Let's take a look at number 8. Now this one here is going to be really difficult. Well, let me hold off on that comment. Let's first of all do our substitution. Everywhere there's a y, I'm going to put an x. And everywhere there's an x, I'm going to substitute a y. Now, next we want to get y by itself. Now, don't take any notes on what I'm about ready to do. Just watch. If I want to get y by itself, a lot of you would bring the 9 over and make it a negative 9 like that, and then factor out a y, so you're left with 3y minus 5. Like this. But that doesn't help, students, because then you'd have to divide both sides by 3y minus 5, and then you would have a y over here on the left side. And some of you might not have understood anything I just did, which is fine if you don't. I'm just trying to show you this is going to be one of the problems. It's going to be really difficult to solve for y. Now, there is a way you could do it, and you would have to do the really difficult procedure called completing the square. And I am not going to make you do that. It would be really difficult. So in this case here, I will allow you just to stop right here. Okay, so there is your inverse function or equation. Okay, moving on to number 9. Here's my x, so I'm going to put a y. Here is a y, so I'm going to put an x. Here's a y, and I'm going to put an x. And look at that, I'm done. That's the easiest one out of all of them. Y is already by itself. There's nothing more I can do. So there we go. Number 10. All right, here's my x. I'm going to put a y and 1/2 y, so I'm going to put an x. And then number 10, just like number 9. Was that number 9, the one we just did? Yeah. 9 and 10 were the easiest ones. There's really nothing else to do. Everywhere there was an x, you put a y, and everywhere there was a y, you put an x, and then we solve for y, but y is already by itself, so no work to do on that one, okay? Okay, let's move on. Next, we were doing numbers, I believe, 25 through 31 odd, and the directions say use the horizontal line test to determine whether the function is 1-to-1. Now, when we say a function is 1-to-1, that just simply means that the given function has an inverse function. You see, not every function has an inverse function. And so we use, if you took notes in class, you should remember this, we run a test called the horizontal line test, okay? And so let me quickly get up something here I can use. There we go. And let's use green. So is there anywhere that I can, whoa, did not want that. Is there anywhere I can draw a horizontal line at all? Anywhere that touches this graph in more than one place? You might say, yeah, right here. Well, no, that graph is understood. It's leveling. It's not really leveling out. It looks like it, but it's still always decreasing little by little. So any horizontal line that you draw on this graph anywhere is only going to intersect the graph in one place. And so the horizontal line test did pass. So the answer is yes. This graph, this function does have an inverse function. It is 1-to-1. Okay, number 27. Well, let's draw a horizontal line here. There we go. And now, is there anywhere that I can put this horizontal line that it intersects the graph in just two places, that intersects the graph in more than one place? Well, yeah, all over the place. Look, if I put the horizontal line here, or here, or here, or here, or here, or here, or here, all of those locations have two intersection points. Now, if I put the horizontal line right here, it's true, it only has one intersection place there. That's true, but that's not what I asked you. Is there anywhere, is there at least just one place where I can put this green horizontal line that it intersects the graph in more than one place? The answer is yes, definitely. So the horizontal line test fails, thus we do not have one-to-one. We do not have one-to-one. All right, moving on to number 29. Look, I don't care where you draw your horizontal line. It doesn't matter. Okay, students, I'm back. Sorry about that. Had a phone call come in. Anyways, this green line, I don't care where you put this horizontal line, it will not hit the graph. Oh, I apologize. I'm going bad on my vision. Excuse me. There are a couple places where you can put this green line that it does not intersect the graph in more than one place. But there's also some places where the horizontal line does intersect the graph in more than one place. And so it only takes one place where the horizontal line intersects the graph in more than one place. And so it does happen. And so this function is not one-to-one. It is not one-to-one. Okay, moving on to number 31. Now this one here is definitely a one-to-one function. I don't care where you put this horizontal line right here. I don't care where you put it. It'll intersect the graph in exactly one place every single time. Okay? Every single time. So this graph is one-to-one. Okay? Or this function right here that I'm circling, yes, it is one-to-one. The horizontal line test passed. Okay? Let's continue on now to numbers 67, 69, and 71. Okay, at number 67, I know you probably cannot write in your books, although if you do, that's fine. That's up to you. But all that you have to do, they want us to draw the graph. That's the inverse of this graph here. And we'll talk about why this dotted line is there in just a couple minutes. But what I want to show you is all that we have to do is reverse the points. So on this graph, 5, 3 exists. So if 5, 3 exists, then on the inverse graph, 3, 5 would exist. And if 2, 1 exists, then 1, 2 would exist on the inverse, okay? And then if 0, negative 3 exists on the given graph, then negative 3, 0 would exist on the inverse graph. And if negative 5, negative 5 exists on this red graph, then negative 5, negative 5 also exists on the inverse graph. Then all that we have to do is simply connect those lines like we're doing now. And then we have the inverse graph. Now, Mr. Earhart, why did they put this dotted line here in the middle? What they wanted to show you is that anytime you have a graph and its inverse on the same coordinate plane, you can draw the imaginary dotted line y equals, let me switch tools here, hold on one second. The imaginary line y equals x, which is, if you graphed y equals x, you would get this dotted line right here. Notice how if you draw a perpendicular line from here, from that point to the dotted line, it's the same distance as this point is from the dotted line. And notice how this point here is the same distance to the dotted line as this point is. And notice how this point here is the same distance from the dotted line as its inverse point is. And that's all they wanted you to see. And that's always true when you have a graph and its inverse on the same on the same coordinate plane. Okay? Number 69, here we go. If negative 2, negative 6 exists, then we have negative 6, negative 2, which would be right over here approximately. And then if we have negative 1, 1, that's going to be 1, negative 1, which is right here. And then if 0, 2 is on your red graph, then 2, 0 would be on your inverse graph. And then 1.5 and 5.3, so we're going to go to 5.3 and then up 1.5, so approximately there. So we're getting kind of the same, it's going to be a very similar looking graph. It's going to come, hit here, curve up, and then continue on. And once again, notice what they're trying to show you with the dotted line. all of these inverse points, like this one and this one, they're the same distance from the dotted line. I mean, theoretically, my drawing is not perfect, but this point here and this point here, they're the same distance from the dotted line. This point here and this point here, they're both the same distance from the dotted line. And this point here and this point here, they're both the same distance from the dotted line. Okay. And lastly, number 71. This looks pretty simple. I guess we'll just have to quickly label some points. Looks like we have, I'll have to get real close to the screen here. Guess I'm getting a little old. My vision's not that good. There we go. And there we go. Well, it looks like we have a point here, and that's 1, 2. So I'm going to go to 2, 1 and put a point here. And then it looks like on the red graph, we also have this point here. I should use a different color, shouldn't I? I'll put this here. And I guess I'll use red for the red graph. So there we go. All right, now let's see. We also have 3, negative 1. So for my inverse graph, I'm going to go negative 1, 3, which would be right here. And that's good enough. It really is. I'll go ahead and get one more point. On the red graph here, it looks like I have 5, negative 4. So the inverse would be negative 4, 5, which would be right here. All right. So I'm going to try to draw a line here that connects all of these points. And we'll have to move it around a little bit. And I'll kind of talk while I'm doing that here. Almost got it. Well, anyways, what I want you to see here is, that's good enough. Notice that again, all the points I'm about ready to circle are the same distance from the dotted line. This point and this point, same distance from the dotted line. This point and this point, they're the same distance from the dotted line. And this point and this point, they're both the same distance from the dotted line. So the green graph is the inverse graph of the given graph. Okay, I hope that's been a help to you. Call or email if you have any questions on the homework.